Hi. I'm going to talk to you about, well, today's topic is what the functional. It's about functional programming, and it's about the what, the why, and the how. My name is Rob Howard. I'm known around the traps as Dan Cabbage as well, and I sometimes scribble on a website, the Rob Howard IDAU there. And so far I've made a career of using the nice bits from different programming languages. I've started with PHP and what have you, and smattering Ruby and eventually some Haskell and stuff in there. So what I'm intending to do today is to try and, in the same way that I pinch the nice bits from various programming languages, I want to try and pinch the nice bits from functional programming so you can use it in your own code in your own languages. Now, all the illustrations today, most of the illustrations today are with JavaScript, but pretty much all this stuff applies to pretty much most programming languages. I mean, hell, you could probably do most of this in COBOL. Maybe not Bash, but you know, if you could try really hard, maybe. But so let's talk about the talk a little bit first. First up, jargon. I want to address this first. I will be using jargon. I think jargon is important and useful, but I'm going to go out of my way though to make sure that I introduce the jargon and make sure I reintroduce it over and over so it sinks in a bit. Because I find that giving a name to a fuzzy concept is very useful. Not only so you can keep track of it yourself, but so you can do your own further looking, read other people's writing, as opposed to having just sort of a general idea. Giving it a name, giving something a name, I think is powerful. This talk is about a bunch of different tools that, much like every other sort of technique salesman, is like a bunch of tools to help you try and make the code more maintainable, less likely to break, etc., etc. You heard it before, so I'm not going to dwell too much on that. I also want to introduce this before I start. I'm going to call this the functional programming functional programming pyramid. I actually stole this from a chap called Lucas de Chilcho, and it's actually the Haskell pyramid, but we're just going to pretend I didn't steal it. So if we assume that your level of functional programming ability or familiarity starts at the bottom and starts and works upwards, there's sort of a level at which you start to become productive using functional programming. And fortunately, it's about there. Like, if you've already seen some of this stuff before, you may already be past it. Like, fantastic. Unfortunately, this is what tends to get discussed on social media or in Slack or in Twitter or whatever. And so you've got this barrage of terminology that's incredibly unfriendly, and a bunch of discussions amongst people who are really familiar with this stuff already. So something to keep in mind. But if you push on through, I think you're going to get some use out of it. So this talk is a little bit like Disneyland, not in the sense of you have to go through Main Street to get anywhere interesting. So there's going to be one bit at the beginning. We've got 6 major sections, but one bit at the beginning that if you've seen any intro to any FP stuff, you would have already seen this. And then I'll try and head off into more interesting areas, giving rationales of things, some examples, etc., etc. So why the hell do I care about any of this stuff? For me personally, the answer is I want to be able to look at a small piece of a code base and understand as much as I can around it without having to zoom back out to look at different areas, jump back and forth, etc., etc. To understand a piece of code, you do need to get the context it's in, and that's going to be required regardless how you write it. But I want to reduce the amount of looking around you need to do in order to understand what's going on. So I've got, here's an example I'll come back to at the very end of the talk, but it's basically a function. And when I'm looking at this, I want to try and figure out what's going on such that I can make assumptions about how pieces of this code works. So in this particular case, this is from something called unblockero, which is, it goes and it just goes through connects to Twitter and unblocks people from your block list. Like when accounts get taken over, apparently, like sometimes they block scattered loads of people, and this is a way to try and recover it. It's an interesting piece of code I found, and it's like, hey, I'll use an example or whatever. But moving on, what is functional programming? Well, functional programming is basically existential equality modular unimportant externalities. It's also known as moral equality, which is defined as I'm so very sorry, and I'm not going to do that again. I'm going to come back to what functional programming is in a tick. First, we need to tackle our first bit of jargon. Referential transparency. Yeah, it's got I hate all the names for these, so I've chosen this one and I'm going to stick with it for the remainder of the talk. Here's an example of a bit of code. It's really simple. We've got a function called double. It's going to take an input. It's presumably going to return something. And for the moment, we're not going to care what's going on inside. And then we're going to use it twice down here. So referential transparency is like a property of code. It's sort of a test you can apply to a chunk of code. So if we can make the following refactoring, if we can take the two, if we want to dry up our code, don't repeat yourself. If we want to only write this once, then if we can make this transformation like so. We pulled up to a variable. In doing this, this is our test. And so if this holds for every instance of double 100 across the entire program, and if we can make that transformation everywhere and we are not able to notice a change in the behavior of the program for whatever metric we care about in terms of the result, the computer result at the end, so stuff being printed to the console or whatever, then it can be said that this double 100 is referentially transparent. So it's all about this transformation. And we'll see how this is going to build from this very basic building block. So the same applies to the arguments. Like, let's take 100, and this is pretty much obviously referentially transparent, but we can pull that to a variable, and it's going to be the same as if, we had made that transformation. So if double is referentially transparent for everything if double behaves in a referentially transparent manner for every argument you give it that is also referentially transparent, bear with me here, we can say that double is pure. This is where this pure function thing comes from. So a sample definition here is just returning x times 2. And it's said to be pure, and we've got a result here. And this decomposed, this pulled apart version is the same as if we'd stuck with the original. So big quote time. An expression is referentially transparent if in a program, all occurrences of that expression can be replaced with assignment to that expression without observably changing the program. Paraphrased from a functional programming Scala by Paul Ciosano and Runar Bjarnason. So all occurrences of that expression, like that double 100, across the entire program can be replaced by a reference to it, like saying, using the variable instead. Without us being able to tell from the outside. We don't care what's going on inside double. We only care how it behaves. That's where I made the joke about extensional equality. Like, this is it. You can tell like externally observable behavior is all we care about for this rule. So yeah. Again, this is known as like pure functions or purity, and unfortunately it reminds me of the preserving the purity of precious bodily fluids. Who's seen Dr. Strangelove in here? I hate the term. I hate referential transparency because it's a mouthful, and I'm just going to say RT now because it's easier, but it's a concept. So on to some more examples, things that may or may not pass referential transparency. So a second one, the same function, and we've got console.log sitting in the middle here. We're saying that this console.log is impure and will be able to be noticed by things both inside and outside the program. It can be said that has a side effect, and I'm going to explain immediately what that means. So we've got double, and we're going to load it up in the REPL. We've got this console.log, which spits stuff out to the console in the process of getting us a return value. The console.log doesn't have any value which represents the printing to the console. It's something that happens off to the side, and then it returns undefined. This is why we call it sort of a side effect. And then the function also happens to return a value. Because console.log is not represented as a value at all, it's just happens. And you'll see the repercussions this has in a moment. So it has a side effect, and it's impure, which unfortunately means that it makes the thing that's inside impure as well, as in because it sort of leaks out. We can tell when you do this rearrangement. So we do this thing, we've got printing it twice, or print it once, so we make the transformation. It's not referentially transparent. Sorry, try again. Another example, where we're referring to a counter from outside the function. It relies on state. It relies on something external, something not in the function argument, something that can change at any time. So if we make this transformation that we're talking about, suddenly the result is different. We've got 200 as opposed to 201. not referentially transparent. See why I hate the name? Okay, so another one, for example, we're also mucking around with state. We're bumping a counter. So I make a transformation, and suddenly the numbers change. So it's not only just reading the state, it's also setting the state as well. It's mucking around with it. Either of these things, mucking around with things outside the function, is going to lead to, unRT code. So another one, for example, we've given append a list, and it's gone and added one to the list, and doing so, it's changed it. We call it twice, and we get a list that ends up with an extra element on the end. And so we make our transformation, and suddenly it's different. So all these things lead to impure. And I'm not necessarily saying impure is bad. It's just categorizing the code so we can then analyze it later. So this mutation is impure, but if we take this code, if we were to take the variable, the list we get in, and then we copy it, and then we push it and return the result, it's now pure. We can't tell from the outside whether it's doing mutation or not. Frankly, we don't care. We only care about the black box. And so this is the basis of a whole bunch of optimizations. So you get a functional, pure interface to things that is efficient internally because it's able to muck around with state, like Immutable.js, which we'll see a little bit later on, for example, mucks around with the state internally to be fast, but presents a pure interface. So what is functional programming? Back to this old chestnut. The bedrock of functional programming is referential transparency and all this purity thing. Functional programming is programming with pure functions, says Runar Bjarnason, and that's the last time I'm going to quote him in this presentation, I swear. So we've got the concept of like these functional languages. If functional programming is a thesis or an idea, like of this referential transparency, then functional programming languages sort of fall on a spectrum in how easy they make it to achieve this thesis, how easy it is to work with things in a pure manner. So you've got languages on one end like Idris and Haskell and whatever that make it working with pure values and functions natural, as in it's the easiest thing to do. And you've got JavaScript, which is also on this spectrum, which, yep, and then there's Bash all the way the other end, which makes working with pure stuff really, really hard because there's no return values, like besides numbers. It's a weird thing. Don't learn Bash if you can avoid it. But what does purity get us specifically? If we ignore all the subsequent things we're going to look at, if we only care about the pure functions themselves, then it gives us this. The behavior of a pure function is independent of where and when it is evaluated, whereas the behavior of an impure function is intrinsically tied to its execution order. So if we take our existing code and just expand it a little bit, it's almost like we've got sort of this dependency graph of things used. So if 201 here depends on the result being calculated, and 400 depends on this result being calculated, and in turn, result depends on 100 being calculated, and so on and so on. So we end up with a tree that kind of looks like this. And so it doesn't matter if this stuff is all separated across the other side of the code base or whatever, or if it's classes calling classes or whatever, if you sort of pre-evaluate stuff, it can be a black box, and it's still going to behave in the same way because we all care about the external behavior as opposed to the guts of it. And it means the nature of these things, because we can evaluate things when we want to, we can then, so for example, if we were to evaluate it in parallel, we can evaluate it twice, and it's the same as evaluating it once. So we can do it in two different threads, two different processes or what have you, where you can do things at the same time, and all you care about is the end result. Or for tests, like pure things are really easy to test in the sense that you can just sort of focus on it a little bit, and it can't tell the difference between you doing the entire calculation or you just giving it the result for the next step in the pipeline. Like you can see there, it's like a tiny piece of the full thing, but you just sort of feed it and pretend it all happened, and then you check the output. It's not saying all code should be pure, but when it is, these sort of qualities happen. So modularity of evaluation aids a few things. It aids in refactoring because we can split things out, put it on the other side of the code base, rearrange them within a function. So long as we've got that dependency tree intact, it means we can rearrange or pre-evaluate or whatever. It helps with testing for the same reasons. We can pre-evaluate stuff. Concurrency and parallelism, we can do it twice, we can do it once, we can do it 300 times, we don't care. Composition, decomposition, you just glue these things and pull them back apart. It just makes it aids in this process. So speaking of composition, let's talk about composition, or Lego bricks. Composition is like you've got Lego bricks, and you've got a few different Lego bricks, for example, and a particular combination is rather useful. So you stick them together in advance so you can then use it with other sets later. I'm going to pre-stick together a bunch of Lego bricks so I can use it to build bigger creations. You come up with a new piece, a combination of two other pieces, and you can reach for that kind of piece now anytime you need it. It's more effective to recognize and use this compound sort of piece rather than separately think about assembling things every time. A composition is combining things in a way that allows you to further combine them. And you can't distinguish the combined thing from the atomic one. So if we've got, for example, the strings A, B, and C, D, when we combine them together, with the composition of those is A, B, C, D. So composing to pull it down and then decomposing to split it back up. You lose the information as to what the original form was, but you can split it back up into different things. It can be A plus B, C, D, or whatever rearrangement you want. And the same deal with functions. You can get calling bar and then giving the result to foo is it's like having a function which does that internally. You can't tell the difference. It's this function composition and decomposition, et cetera, et cetera. Like npm JavaScript dependencies, npm version 2, that sort of naively composed. You just had trees and trees of dependencies and you stick them together, and a bunch of things composed, but I really need to kind of move on to the next section. So, expressions. Expressions got a quick mention in that first Runa quote. Hold on a minute, sorry. So, if we've got a function here, well, this expression, sorry. We've got a value, which can be things like strings and numbers and objects and lists of whatever. And then we've got a function here, for example, where it takes arguments or whatever, and where we can evaluate them to equal a result. In this case, it's 4. When I say evaluated, I mean substituted. For example, we've got our x, and we substitute the x equals 2, do the replacement, everything fades away. Then we've got our 2 times 2, and multiplication is a function, so it's got 2 arguments. We're going to substitute it internally in the guts of the language somewhere to get 4. Evaluation is simplification. And surprise, this is referential transparent, this particular one, because we can do all that substitution and not notice. So expressions are made up of values and functions, and I kind of fibbed a little bit because I said values are strings and whatever, but functions are also values in a number of languages, including JavaScript. Also, if you're interested in going down a particularly large rabbit hole, values can be represented with only functions. This is also known as lambda calculus. Not doing it this talk. Moving on. Functions are also values, which gives rise to this sort of stuff. We've got we've got a function value here, and we're going to assign it to a variable, and then we've got a list, which is we're going to give this function to another function, map, like so. And so this map is known as a higher order function because it's a function that takes a function as an argument. So when we've got all these pieces, let's put some pieces together. A desire for referential transparency, as well as like the helpful feature that is functions as values, and abstracting a common behavior with function composition and decomposition gives us these things, which are kind of familiar to, or it might look familiar if I phrase them like this. They're just a sort of building block combinators, because these aren't necessarily inherently functional. This is kind of functional style, but that's fine. It's basically the building blocks push us in this direction to end up coming up with these little combinators, these little functional helpers that we can glue together with function values and whatever to make these things. And we've got a bunch of other ones that are array specific in JavaScript, but this sort of stuff applies to a whole bunch of different data types, as we might see in just a moment. So we've got a function here that we've written in very much the imperative style, which is fine. And basically it's going through all the birth years, and it's getting the ages for each one, and if their age is over 20, then we're going to add those together. It's a bit nonsense, but you know, what you're going to do. I get to make up the examples because I'm here, right? But mystery code, when given in using this more functional style combinator stuff, is birth years, and then for each of the birth years, we're going to map over it. We're going to map is a function that will apply this function, this birth year, taking birth year as an argument, this year minus birth year, that it's going to apply that function to every element in the array. It's going to preserve the shape, preserve the length, and that's how map is designed to work. We've got filter, which will take an array and reduce it down in size depending on the evaluation of that function that we're given it, and then reduce, which can go from list to anything. Reduce is also known as a fold, and it's one of the base building blocks. If you want to, you can build map and filter in terms of reduce, but that is an entire thing in its own. So I'm sorry, this code is getting gradually smaller and smaller. It's going to stop now. But you know, when we've got because the correspondence here, we've got the for loop, which is showing up in terms of the map, and also the filter, and also the reduce. Like it's basically this is all these three combinators have, or these helpers have, are doing the loop over the array in their own right. And then you've got the functions themselves, which are doing it's like we're basically pulling some pieces out of the imperative style stuff at the bottom to hopefully make something that is more understandable. This is entirely a subjective judgment. I personally find this easier to read. Some people may not. That's fine. But yeah, we sort of pull bits out to give us the result, and finally a return. The top one is returning an expression which is going to evaluate to a single value. And we've got the bottom one, which is returning the value that is being calculated based on a bunch of mutation. Anyway, so hey, I bet someone's noticed that I'm looping over the thing like 3 times, and that's really annoying. Yeah, this code by itself will loop over the array 3 times, and it's like, oh yeah, okay. It looks a little more readable to me, but at the expense of it's traversing it. So there are different ways of doing this. Jumping over to Ruby, I did it for 4 years. I've got to put one example in here, come on. Where I've got birth years, which is an array, and then I've got this little .lazy thing. Now, this could very easily happen in JavaScript. You can go and write one in a REPL afterwards if you really want to, but it's part of the Ruby standard library where we want a lazy version of something that when we go and apply its versions of map and select and what have you, work in such a way that it will apply all the functions for a particular element as it goes through. It will only traverse the array once, and it will apply things. It sets up some computations and then goes bang for each element. Does all of them in one go, all in one go. It's like basically building up a bunch of instructions to then go bang whenever you actually want the real result out at the end. It's a way, it transduces from closure is I think a way of doing this. Fusion and Haskell, it's all very much the similar concept. You're building up sort of the lazy sort of things to apply later. So some languages are entirely expression-based. I'm going to blaze through this one because I don't really want to go into much detail, but we've got, main is a function. This is sort of pseudo-Haskell. But we've got main that's, a value which is made up of a bunch of expressions. We've got users with, which is a function that takes a couple of arguments. We've got hackers, which is sort of effectively a constant. And so it's an expression, so we can simplify it. We'll just sort of, pull pieces in, just keep pulling pieces, reducing, until we're left with basically telling the Haskell runtime, in this case, that we want to print a value that is 2. So this is not like, hey, here's a practical thing you can do. It's like, here's an idea of how some other languages operate. Expression-based, very FP-ish kind of languages can work like this. So speaking of languages, language affordances. If everyone remembers that functional languages spectrum chestnut I introduced earlier. So this is kind of like the previous example we had, with a list of things in the map, filter, and reduce. So if I were doing this only in terms of functions and values, then it would probably end up looking like this, which is, I personally find this a little more difficult to read because you have to go to the map. It's like it's backwards to start with. Then you do the map with the thing and then take the result of that and give it to the filter, and then take the result of that, give it to the reduce, and it's like all right, I've got a staircase down and then work my way up to understand what the hell happened. So some languages have affordances, make it easier to do certain kinds of programming. Elm lets us, for example, do this, just work with functions, but we've got this pipe operator thing. And when I say operator, I mean it's a function. It's a function that has a funny name, basically. And so there is affordances within Elm, within Haskell, within a bunch of other languages to let us come up with these operators to let us work with these function pipelines more easily. We don't have that option in JavaScript, so which gives rise to, and same with Ruby and Python and PHP and what have you, and so it gives rise to something what Gary Bernhardt calls faux O. So it looks like OO, but it works like FP. So if we were to invent our own array thing, you make a new myArray, you give it some items, and we've implemented map for this. I'm using the class syntax, so just in case you don't really know JavaScript, but you know Ruby or C#, it's a little more familiar than .prototype. But anyway, so we're constructing a new one, and we've got a map function, and internally that's going to go over, it's going to look at sort of the object's kind of state. We set it up, and it's been populated with some state in this constructor here. And then in the map, we're going to look at that state. We're going to iterate over it, and we're going to apply a function that's been given to us, because it's map, and we're going to take the result out and stuff it in a new array. And then we're going to return a new myArray with those items. It looks like OO, but if we use it like this, we've got this transformation that we love to do. We pull it out. It's referentially transparent, but it looks like OO. Yes, best of both worlds. So we get a little bit of a UI. We sort of take advantage of JavaScript sort of OO bias kind of UI to produce this kind of code. So we can make entire libraries of this stuff like functional combinators and things. And that's what Sanctuary, Folktail, and Ramda are all about. Basically, sort of faux O kind of sort of functional helpers and values and whatever that's JS friendly in its user interface, as opposed to big compositions of functions that are really hard to follow what's going on. So, photo. All right, cool. So, all right, I'm going to keep going. Immutability, this will be quick. I wrote a function. I'm really proud of this function. I'm so proud of it, I called it twice. It's big list. It takes about 40 seconds to run, and it produces the numbers 2 through 12, or something, or 1 through 12. So because it takes ages to run, I want to, we've seen this before, I want to try and pull it up here, and it totally works the same, right? No, it doesn't. Something went wrong. So it turns out that even numbers is a terrible function, and I should be ashamed of myself, because you don't understand the details of this, but somewhere in the middle of it, it's stuffing around with the array. Now we saw this earlier in the referential transparency examples. So because it's stuffed around it, we've given it a list, and it's like, you've lent your lawnmower to your neighbor or something, and they've gone and mown the lawn, and they've taken out the engine and given you back. It's like, thanks. That's fantastic, mate. So similar deal here. We've given something, and it's like it's changed. So let's try and imagine a world where this doesn't happen. And we can try and achieve this through a few different ways. One is the quality or sort of property of the code. So if something is referentially transparent, then it won't be doing this. Or there can be a language restriction. For example, Haskell, Elm, Reason, I think. Someone please correct me if I'm wrong. Will basically enforce this at the language level. Will say it will not provide a way, unless you use an escape hatch somewhere, will not allow you to mutate a variable. Which means it can go and do other things like optimize the hell out of stuff so it seems immutable but is actually mutable under the covers. That's an entire other thing. Or through API restriction, not really providing a way to, without throwing an error, or not providing a way at all to sort of mutate the data. So if you've got seamless immutable or JavaScript library, what it will do if you wrap it around a list, if you try and do something that's mutaty, it'll throw an exception at runtime, which is fine, and says, no, something went wrong here. It's in an effort to try and catch this sooner than later, catch this sort of error sooner than later. Objective freeze is another way of doing it, except it's got limitations where, if you're dealing with objects, it doesn't quite do it. So you've got a couple of different options for doing this via the API restriction route. One of them is seamless immutable, which is like preserving all the UI for working with lists and a bunch of other things. But there's also immutable JS, which is a strange alien beast when you try and use it, but it allows you to have maps and sets and lists and But it's got a very different UI and doesn't expose a way in the UI to actually change stuff mutably. It's like it's taking a different tack. It's not like I'm going to open a door and then slap you if you try and walk through it. It's a case of there's no door. So anyway, but it's also a little, like some people find it really Byzantine and difficult to work with. So whatever, try it out. If it works for you, fantastic. If it doesn't, So effects as values, our next major section. Effects as values is the idea of representing impure actions as values that can make them pure. So representing impure actions as values can make them pure, or representing impure actions as instructions to be later interpreted can make them pure. So bear with me because I have a silly example. I'm full of these. If we have something that, say we've got the idea, or we want to represent the idea of printing a message out to the console. We've got a function that will construct a value which represents printing something out. And we have something which will, one of many, potentially many sort of interpreters that will take this thing and then do something as a result of it. This could be one thing that prints out to the console. It could be another one that could be pure, another one which sends it over the wire to a radio transmitter, like whatever. And then finally at the bottom here, we're going to make hi, which is a value representing the idea of printing out a message. I'm trying to make this less long-winded. So we're going to squish it up and keep going. So we've got hi. That means we can make an array of, we can start treating this like a value, like other sort of pure values that we already have. So we can stuff it in an array and say, hey, this represents printing out hi 4 times. So squish that up. And then so we can have, and then later on, we can then, a separate area of the code base maybe, have this thing where we go and loop through the messages and we evaluate the message. Evaluate each of the messages in that list. We had the instructions, and separately later we're going to interpret them to be something that is actually effectful, something that has side effects, like console.log. So this bit's pure, this bit's not, and the two shall not meet, or whatever. So they could be right above each other, they could be on other sides of the code base. As I was saying before, modularity, you have a lot more flexibility in terms of where you put this thing now. I'm aware that this particular example seems really ridiculous, but it is real. I use this stuff every day, and it's really nice once you get the swing of it, but it's utterly alien when you haven't seen it before. So here's another library, another example. A Future is an unfortunately named library doing Fantasyland Future. Funny name. It's all good, whatever. But it's or there's other ones like data.task, but they all sort of represent these things that will happen in the future. It's almost like promises, except we'll talk about promises in a tick. But this is something that is doing the fetch and returning a future value. And so, we're going to do stuff as a result of that. We're going to have values that use the earlier pieces that we defined or whatever, and I'll step through this in a minute. But we've got a pure piece here that's all about the instructions for if we were to do something kind of asynchronous, what would we do? Separately to we're actually going to go and do it now. So we've got again, keep separating the pure stuff from the impure. So if we create a future here and then we .map being a generic name here, as in with the contents of with the results of the future. It's a .then for this. It perhaps should be called .then, but with .map, we're going to get the result and then we're going to pass the HTML out using the response we've gotten back from the URL. And then separately, we've got linked pages which will use the idea of fetching the thing and passing the HTML out. And we're going to use that to scrape a bunch of stuff and do it in parallel. This is all just the idea of doing it as opposed to an actual it's going to do it. Like even the .parallel bit is still values representing potential computation stuff. And then we go and fork it, and we say that if it throws an error, if there's an error in the thing, then we want to bubble up the error. Otherwise, we're going to take the result and save it to the database or something. It's very made up. But yeah, basically we've got it means we have flexibility. So promises, unfortunately, as soon as you go and create this stuff, promises, as soon as you write it down, as soon as you execute it, the horse is away and over the hill, and you're furiously like, oh, wait a minute, I'm just going to try and close this gate. goes and does stuff. It just, fires the missiles. It just goes, as opposed to, whoa, I want to do some stuff. I want to maybe muck around with this first before I go and do the thing. And also, it's got the idea of this sort of resolved value. In this case, I've got linked pages and linked HTML that are using eventual HTML twice, and it will evaluate it twice, which is either a good thing or a bad thing, depending on what you're after. And if we want to cache this, and we can chuck an extra cache wrapper around this that Future provides, where the flexibility is saying, evaluate this multiple times, evaluate it once, with the flexibility there. So for this very specific example, sorry? Mm-hmm.
It sounds a bit like deferred execution.
Yep.
Anyway. Is that along the right lines?
So the question was, is this a deferred execution? It really has to say something like C#. Unfortunately, I used C# before Link existed, so I'm really not the right person. But it's the idea of, deferring the execution, but it's also, in this case, the idea of representing something that is effectual as a value. It just so happens that async is the burning question on most JS devs' minds, including myself, and so it's a somewhat relevant example. But this, as I said, with the messages thing, you could equally have something that represents sort of the impure stuff. For example, actually, no, I'll come back to that. But yeah, Fluture and data.task are examples of this particular async thing, but it's a very general idea that applies to a bunch of different contexts. So now onto the potentially controversial bit, which, depending on the circles you move, it could be, this could be nuts and a bad thing, or it could just be business as usual. Everyone's coming from different areas. I came from a PHP background via way of Ruby and other sorts of things. And some people come from like entirely C# or Java the entire way, and this is like, of course I want types, but we're going to go through it regardless. Probably a little bit quickly, but we will. So I have this problem where I write code, and I write terrible code. This is one example. I've got my utils, and it's going to reverse a string, and of course it's going to explode because undefined is not a string. It's also going to explode if I feed it 7. So this is going to explode if, well, we don't know if it's going to explode. We don't really know. We've got no way of telling. The only way we really have it telling is sort of the name. Sort of guess the name, then go and read and dig into the code to try and figure out what it's actually doing, to see if it lines up with what the name's saying is, or what the documentation says, etc. So let's look at the string reverse function itself. We've got a parameter x, and given the name and what we're doing with the function, we've dug into it. It looks like it's a string. Anyone calling with this number is, a bad person. They should feel wrong. Or should feel bad or whatever. But it'd be really nice if we could tell the computer what we mean. If we give the computer more information to help us. And so there are some tools that let us do things like annotate things with, a string or whatever. And, if you use it the right way, it'll pass. If you don't, it'll explode, etc., etc. So I'm using Flow for this particular example, but there's a few competing ones, Flow and TypeScript. And if someone knows Google Closure, because I don't, I'd like to speak to you afterwards so I can be across this stuff. But for example, I've got my chunk of code, example.js. I'm going to check it with Flow, and I've got no errors. Yay! And then I run the code, and it produces hello backwards. Fantastic. I chuck a wrong value in, and it has a big sad, exactly as I expect. Great. So, you've got strings, you've got, arrays of numbers. You've got punching holes where you've got like the idea of generics, or it's also known usually in FP land as parametricity, where your jargon, where basically this function is not allowed to know what t is. You can't do reflection on t in most languages. It varies as to whether, like, some type systems don't let you do it intentionally. I think C# is one of the ones that don't let you look at t. Java is one of the ones that lets you look at it. I would love to also chat with some C# people afterwards to make sure my assumptions are correct. But basically, it says the t is determined by the person who's calling it. By the code that's calling it determines the type, and the function itself is not allowed to make any assumptions at all about what t is. It can't add a number. It can't add 1 to every element in the list or anything like that. It's not allowed to know intentionally. It's got blinders on. So this works, and fantastic. We can go further. We can have things that are particular object shapes. We've got this thing here that is a way of saying, you know, this thing is intentionally a string or potentially undefined, whereas usually it'd be a string and only a string and no numbers, no undefined, no null, no nothing. We've got ways of saying, you know, a type is this thing or this thing. Who in the room uses Redux at all? Yeah, okay, well, this might look a little more familiar, sort of Redux reducer. We've defined this particular shape, and it can be either this thing or it can be either that thing. And so the computer will help us, in this case, Flow will help us check that we are using each one properly. So if we end up with a logged in thing, then before letting us use action.user, we need to have proven that action.type is logged in. We need to make sure it's the first option before we're allowed to use the guts of it. Otherwise, if the second branch called .user, it's not there. Like, it's undefined, what's going on, it's just basically broken. Whereas if the code here is checking, Flow here is making sure that we've verified, we've proven to the compiler or the type checker that we're able to get down a certain path. And this is all decisions made by the different type checkers. It's not inherent to type checking, it's just something you've chosen to do. So back to our first example, we've put the string there, but these tools to varying extents can infer some of this information for you such that you don't need to write the things. Sometimes you write it only on the outer edges. Flow makes you annotate every external facing module, whereas it will infer inside. TypeScript, I still have trouble figuring out the inference rules. Sometimes it will, sometimes it won't. I got to get better at that. But anyway, so these are sort of a small family of tools like Flow and TypeScript, glue closure, as I said earlier. So what's this doing in a functional programming talk? Why am I talking about types? God. So it all comes down to expressions. Consider a language where everything is a composable expression. We saw one of those earlier. Where everything, including effects, because remember we can express effects in terms of pure values, things that stand in for values. If things are expressed in return values, it means that we can suddenly the return values of the function describe a lot more about how the code works. Because the type system is describing more about how the program is put together, suddenly you can rely on it a lot more. You can have it do things like checking if something is referentially transparent or not. This is basically the idea behind Haskell. If you've ever been curious about what the hell that thing is, this is basically it. Everything's pure, effects is values, really strong type system, chuck it together, fantastic. So I kind of jumped over my bio at the beginning deliberately because I want to explain some motivation stuff here. I went through BASIC and PHP for like I did PHP for a good 7 years or something with JavaScript throughout that time as JavaScript evolved, which was an interesting process. And then I had troubles with the community in terms of making sure my stuff worked. It's not inherently a problem with PHP, but at the time the PHP community was not very interested in anything like testing. I really cared about making sure my stuff did not break. I wanted to use the computer as much as I can to help me with that. I asked a PHP meetup, like, who here in the room has used PHP Unit before? And I got 3 hands. Who's used it at work? No hands. Like, it's gotten a lot better. At the time, it kind of sucked for that. And so I ended up moving to Ruby because of the strong testing culture. I really wanted to make sure my stuff didn't break. And so of course you write tons of tests to make sure your stuff works how you think it is, was sort of natural for the Ruby community. And so I really enjoyed doing that for a while. I wanted to make sure my stuff didn't break. And so over time, though, I found myself writing a lot of tests to make assumptions about my code. It's almost like you're trying to prove a negative. Like you can test some positive cases and some select negative cases. It'll probably break if you call it this thing, but you can't possibly test everything because you can feed anything at any point. You just be writing tests and tests and tests forever. And particularly when it comes to refactoring, I found that I'd either have to take tiny mincing steps where I'd write tons and tons of tests to do like a larger scale refactorings, or I'd basically do the leap of faith across the gap and write tests for the other side and hope to God I kind of made it. It was unsatisfactory for me in that regard. I loved the rest of the Ruby experience, but that particular bit really got me down to the point where I ended up jumping straight to Haskell. So my entire experience with my motivation for this business has entirely been about types, and the functional program bit sort of happened as a result of that. The stronger the types, strong type systems seem to naturally lend themselves to functional programming. Now, Rust and stuff exists with its own strong typing system, and that typing system is fantastic and describes a set of behavior, and the Haskell type system, some other things describe another set of behavior, and that's fine. I ended up jumping to the Haskell side of things to get strong types. FP kind of happened, and then I started to introduce FP. Sorry, appreciate FP over time as I got more into it as a community. To the point where I'm now using something called PureScript on the front end. If I was starting in JavaScript, this is much later after the Haskell, I would probably be starting with Elm instead as a way to try and get more familiar with this stuff. And I encourage anyone who's vaguely interested in like experimenting with stuff to try out Elm. It's really interesting. All right, I'm going to wrap up this talk shortly with a couple of things. The competent programmer, I don't really like the tone of this quote, but I really like what he's getting at. The competent programmer is fully aware of the strictly limited size of their own skull, and God, do I feel it. I'm fully aware of how many stupid mistakes I make in the process of writing code. So I want to try and reduce the amount of things I need to think about at once. I want the computer to help me as much as I can, and I want to reduce the amount of context that I need to focus on a particular piece of code. I want to zoom into a piece of the code and try to try to block out the rest as much as is practical. So, like, I was looking at this chunk of code, and because things have been written in a referential, transparent manner, I know that just evaluating this won't launch the missiles. It won't send the horse bolting or whatever. Immutability means that the values I lend to other functions, I'm going to say lend because like please don't muck around with them. I need to use that, like client or auth details and things. They're not changing because of immutability, and again the referential transparency. We've got effects as values that are building up, preparing for something. In this case, we're just returning the instructions that are later going to turn into something. And then types, so I know what my inputs are, and so I know that I'm using the rest of my application correctly without having to go look at it, without having to dig into the implementation details of these things. So, further things to look into. I did a functional programming talk, and I didn't want to talk about recursion because I write Haskell as a day job, and I don't do recursion very often. It's like everything FP is recursion. Well, technically under the covers, but I don't really notice a great deal of the time. So, or currying, I didn't do that either. Continuations are ways of representing sort of stepped computation, things you partially evaluate. If anyone knows about generators, continuations are kind of like the functional version of that, where you want to stepwise represent things. Asynchronous stuff is very nicely modeled with continuations, or lazy trees and things. It's just, there are a bunch of things that were represented by this idea of continuations. You've got pattern matching, which is the decomposition thing I was talking about for values and other things. It's it may eventually end up in JavaScript. There's a stage 1 proposal. I don't know if does anyone know if it's stage 0 or stage 1? If anyone, no, okay. But there's a pattern matching proposal. Really, it'll be interesting if it gets through. I hope it does. Things like parser combinator libraries, when you want to consume and understand a particular string a different way. Instead of reaching for a regex, parser combinator libraries are basically building up this sort of string processing things out of little functions instead. And it's something to get into. There's a library called Eulalie that E-U-L-A-I, anyway. At the very end, I'm going to be putting something on my blog after this with a bunch of reference links as jumping off points. And this is going to be one of them. If you want to dig into maybe something that isn't a regex is like more interesting sort of as an experiment to learn about, to perhaps even use in real code, it's up to you. Elm, Haskell, and PureScript. If this is all completely new to you, I highly recommend Elm as something to muck around with. There's also the Haskell book, or Haskell Program from First Principles, if you really want a deep dive, because it covers some of the little bits, like the little depth of lambda calculus that's useful. It's a chapter long, it's a short chapter, but the idea, like learning about that, helps you understand other bits in a sort of more, it's an abstract way of describing a whole bunch of things, and so it's useful to be aware of it, even if you'll never actually write some production code you don't use a lambda calculus in production. It's just a tool to help you understand how some things relate to each other that may not have previously seemed related. And lastly, functional call, an imperative or effectual shell. is the idea that Gary Bernhardt presented in his talk Boundaries. And it's basically a way of, it's saying that when we're writing functional programs in things like Ruby, in this talk's case, equally applies to JavaScript, Python, PHP, or C#. It's trade-offs between making things pure and making things effectful, and you do really want to touch the outside world sometimes, but the idea is to try and centralize to have as much of the pure functional stuff doing the business logic and really having this sort of thin shell on the outside doing the web handlers, the queue wrappers, the effect interpreters, and that sort of stuff, interacting with the outside world there. And his idea was 80% functional is better than 0%. You don't have to get to 99%. It's, it's just kind of, it's useful to try this as a trade-off between the two different styles and see how it works for you. Cool. Well, thank you very much.